Okay, so let's have a look at section 10.2, iteration. So iteration is just one method of finding a solution to f of x equals 0. So identifying, locating roots, like I said, to the equations that are potentially very difficult to find the solutions to through algebra. So the method is, first of all, you must start with an equation f of x equals to 0. So if it's not arranged in that form, you've got to rearrange it. Then you are manipulating it in such a way that you are getting an equation x equals to another function g of x. So that must be written. And then you're going to use the iterative formula x of n plus 1 is equal to g of x of n. So if you've got a starting value, you substitute it into the function g function, and then you have to obtain the first approximation. Then you're going to substitute that back into g to get the second, etc., etc. So to solve this equation, you could have different situations using the iteration formula that you obtain. So you can actually rearrange certain functions in various ways to obtain different iterations, and they could be leading to into a solution, or which means that they converge to a solution, or they might lead to bigger and bigger values. We call that they diverge. So there is no solution can be found using that particular iterative formula. Also, it depends on what is the starting value. So over here, the idea is to give you an example. Obviously, we could solve that quadratic, but just to show you how iteration can be shown to converge to a solution. Okay, so the first thing is to rearrange it. So you get x squared minus x minus 1. And because you are solving this equation, so you're finding the roots of that equation. So one way of doing it is to write it as x squared is equal to x plus 1. And then let's say x is equal to square root of x plus 1. So we're going to look for the positive value. So that means that the iteration you could be using is xn plus 1 is equal to square root of x n plus 1. Now graphically, what you can do is you can think of that as drawing the graphs of y equals x, which is the straight line going through the origin, and drawing the graph of y equals root x plus 1, which is partly drawn over here. So having drawn those, you could see that they will be equal to each other at that point, so that's the root. Now imagine using that iteration formula. This one will give you an example of having staircase diagram which converges to this solution. If we start on a particular, correct value of x. So let's say we start somewhere here. So that will be your initial value that you're going to start. And what you're doing, you are substituting it into the right hand side. So that's your x0 that is going to go into this equation. Once you've sub it in, you're going to sub it into this function. You're going to get this answer, which is x1. Okay, that's going to be that value over here. But why is it x1? Because when you move it across and then you sub it back in, the y is equal to x. Your y values are going to become the x values. So you've got x1 over here. Now the next iteration, what it does is allows you to repeat the process, and you're going to substitute that x1, so go back again, and you're going to sub it into the curve, and the curve is going to generate its y value, but that becomes the x value once you put it back into this equation. There you go, and that is going to be x2, which is the same as the y value over here. The values are the same because this is the line x equals 1. And then you put it back in, and you could see that you are creating like a staircase. So those answers, they're going to be popped, x2 is going to be popped back into the curve. You're going to get the answer, which represents square root of x2 plus 1, and you're going to obtain x3 by making it hit the line y equals x, then going down, and you're literally zooming closer and closer to the solution pretty quickly. Okay, so that's, within a few iterations, you are going to obtain the answer close to that solution. Now that's called the staircase because they look like stairs. Now another situation you could have is you can obtain a converging cobweb situation, cobweb diagram. So then iterations will approach from both sides, so they will alternate. If you could see in the staircase example, they approach from one side. They could approach from this side. If you maybe started here, they could approach from that right. So let's have a situation with exactly the same equation. So f of x is equal x squared minus x. Now let's actually rearrange it in a slightly different manner. So let's obtain a different iterative formula. So let's actually separate, let's move, we are solving f of x is equal to 0. So x squared minus x minus 1 is equal to 0. So let's separate the x's from the constant term, and then factorize x, and then rearrange it to actually obtain this lovely reciprocal graph, which I've already sketched. So changing it into the iterative formula, you've got xn plus 1, and then xn is on the right hand side. So therefore I sketched the line y equals x and the reciprocal graph y equals 1 over x minus 1. The solutions of making them equal to each other, so this equation is where the two graphs intersect. You can see that you can use it to find that solution or this solution over here. So let's imagine trying to find the negative solution. So you could imagine starting off with some value of x0 over here. And you can see that when you sub it into the curve, it finds the solution over here. Now that goes across to the line y equals x. So that any coordinate on that line, coordinates of any points on that line will be equal to each other. So over here, that value will represent the y solution, but that becomes the x1 value because, and now that x1 value is going to be substituted. So that, so far what we found is x1. So that would be obtained by substituting x0 into this equation. Now you've got x1, you substitute it into this right reciprocal on the right hand side, and that will become, so you get the answer over here, and that answer is your y value, which is this one. But when you make it bounce across, it will hit the line, okay, and it becomes x2. And then that can be used to obtain x3 in the exactly the same manner. So you're putting it back into the curve over here. So you're hitting the curve first always, then you can see you're going to hit the line. You don't need to go all the way to the y-axis, but that value here is the answer to 1 over x2 minus 1, and that becomes, because it's exactly the same as x value, that becomes your x3. There you go. So you've got there, and then you make it into, put it into the curve. So if I go over it with a green, you could see very clearly that we started off with this journey over here, then we went all the way across over here, then we hit the line, then we hit in the curve, then we're hitting the line, then we're hitting the curve, then we're hitting the line, then we're hitting the curve, and you're going to zoom in closer and closer to that solution, which is the x coordinate of that point of intersection. And that's simply using a different iterative rearrangement of the same equation, x squared minus x minus 1 equals 0, and that allows you to find the negative solution. And you could see that the cobweb diagram is getting closer and closer to the solution. Now, of course, you could have a situation where the solutions cannot be found, so you potentially could find another rearrangement of this equation. So let's actually rearrange it. We're separating x from x squared minus 1. So you could have x n plus 1 is equal to x n squared minus 1. Now imagine starting from some value, maybe x equals 2, something positive here. So as soon as you sub it into the right hand side, so into the curve, there you go, you obtain the value of y, which is then going to become what the value of x that you're going to use in the next instance. So that's your x1. And then you're going to sub it again into the curve. And it's like a staircase, but going in the opposite direction. So you're going to alternate between the curve and the line. And you could see that those, you're going further and further away from that solution. So this means that this iterative formula, when starting from the right hand side here, so starting from x0 equals 2, for example, will clearly diverge. So no solution can be found using this particular arrangement. Okay, so let's have a look at example 4. So in the example 4, there you go, we have got a function f of x equals x squared minus 4x plus 1, and we are asked to show that the equation f of x equals 0 can be written as x equals 4 minus 1 over x. So my advice to you is to actually start from the arrangement that you are aiming for. So start from the answer. So start from the answer. Okay, so we're going to start from that and then rearrange it so it make it look like this. Okay, so we are going to make it look like x squared minus 4x plus 1 equals 0. Okay, so the first thing my instinct tells me is to multiply everything by x. So I obtain x squared on the left hand side and 4x minus 1 on the right hand side. All I need to do is now move everything onto the left hand side, and that is your f of x equals 0. That's the easiest way of answering those questions. Lots of people advise to actually rewrite it from, if you have time, in the correct order, but this time moving forward. So we multiply by x, so you get x is equal to 4 minus 1 over x, and you say shown. But usually, as long as you finish with f of x equals 0, you will get your marks for having that rearrangement. Okay, so in part B, we are going to use this iterative formula, starting with x equals 3, to find the first 3 approximations, well, of first, including the next 3 approximations, if you assume the first 3 is also an approximation. So x1 is going to be 4 minus 1 over 3. I like to show that I'm substituting this at least once. Actually, I put x0 first and then write it like this. So this is going to be the answer, 3.6 recurring. x2 Okay, the next ones, you don't need to necessarily show all the substitutions, maybe just to show that bit. So let's type it into the calculator. So 3 equals, and we're going to do 4 minus, and then we have 1 over runs. There you go. So that was our 3.66. Now if I press equal, that answer is going to be substituted into this equation. So there you go, and that gives me 3.72 recurring. Okay, let's substitute again. So all I need to do is press equals again and obtain the third answer, 3.73170, 7317. There you go. With this one over here, normally with these answers you'll be asked to give your answers to a certain amount of decimal places. I don't think they're worried about it in this particular example, but just bear that in mind. Okay, so now let's move on to example 5. In this example we've got x cubed minus 3x squared minus 2x plus 5 being our function f of x. Now we have to show that there is a root between 3 and 4. So you've got to substitute 3 and then substitute 4. So traditionally I like to show that at least substituting it properly once. Obviously everything will be done with a calculator using the ans key. So put 3 and then put the rule with ans. So ans cubed minus 3 ans squared minus 2 ans plus 5. Okay, so the first answer is minus 1. That's clearly is a negative. Let's put 4 in. So put 4 equals, then scroll up and then make it work it out to give you 13. That's clearly greater than 0. So what you want to write down, so you could say f of x is continuous. There is sign change, therefore, which can be just those an equal sign with an arrowhead. Therefore, root, if you named it as alpha, you could say the root belongs to the interval 3 to 4, or is between 3 and 4, or you could say root is between 3 and 4. Like I said, if you named it alpha, you can stick alpha there. Okay, so for part B, we're going to use this rearrangement to calculate the approximations x1, x2, x3 if our starting value is 1.5. So we're going to find x1. Like I said before, I like to substitute it at least once, so it's 1.5 cubed minus 2 times 1.5 plus 5 over 3. But I'm going to use the calculator to find all the others, well, this one and all the others in a quick way. So we're going to use ans to the power of 3 minus 2 ans plus 5 in the numerator. In the denominator we've got 3. Okay, so the first solution is 1.33853. Okay, next one, if I press equal, I'll get the next one, which is 1.2544477, and press again, it's 1.220004478. So it seems to be converging, hopefully. I've not been asked to do any more, but if you do press it again just to check whether it does converge, it seems to be, yeah, it seems to be doing something. There you go. had to do it a fair few times. Okay, so let's do the second, exactly the same iterative formula, but this time starting with 4. So put 4 equals, scroll up, let's substitute it in. The first value I get is 4.50924. Press it again. Oh, it's getting to 5.405848. Press it again. It's getting to 7.121901. So this seems to be maybe not converging. Let's just double check. Okay, yeah, it's definitely getting. You see, if I carry on for a bit more, so this one is divergent, but this one seems to converge. So this one diverges from a solution, this one is does converge, divergent. Sequence, if you like. Okay, so that takes us to exercise 10b.